All right. Good morning, everyone. So this is our eighth session. We will be reviewing all the topics that we discussed during the last 2 weeks briefly, and I'll let you guys work on some examples. Right. So as we discussed before, we're going to do a class activity reviewing all the topics that we went over, but it's take as long as you want. I just want you to fully go over the topics because we have a project due next week. So please take your time. If it takes 30 minutes, take 30 minutes. If it takes an hour, please take an hour to finish all that. Yeah, that's just all I want. So please do that, and we will start the review now. All right, so let's review. Okay, sorry. All right. Okay, sorry about that. That was for my tablet because I'm writing on a tablet. It's causing me some problems, as you know. All right, so let's do some review. So review. All right, so we're going to talk a little bit about everything that we discussed so far. So let me just give you some ideas that we've been covering so far. All right, so let's talk about population first. Right, so population is pretty much everything. It includes everything that is included in the topic. So for example, if we're talking about um, what should I say, the water usage, right? For example, we're talking about water usage in liters in Tanzania, then we have to measure all of that um, at a given time. But population is it's it's doable, but it's very, very, very hard to do because how are you going to measure all water usage in Tanzania at a given time? Like say, for example, if you're getting a sample from one region, it might take, I don't know, a week to complete all of that, and by the time you finish all your surveys, your first data will be outdated, right? And we don't want that to happen, and that's really really hard to do. So we call this, say, let's say average. Let's say average water usage in Tanzania. We call this Greek letter mu, and we read it mu, right? Mu theoretically exists. We know for sure that there is an average water usage in Tanzania, but we just don't know the exact number for sure because then we would have, I don't know, like hundreds of thousands of people taking the samples at the same time, and it's really hard to do, right? So what we do is we take a sample. Um, for example, we take a sample from from which is a portion of population, and we just hope that this represents the population correctly, and we call this what? A sample. And if we say the average water usage in liters, we call that X bar, and we call this sample mean. All right, so in this class, um, we are mainly dealing with the sample mean because we are never there. In reality, we're never gonna find the mu. We cannot find the mu at a given time because it's virtually impossible. So we call this parameter. Okay, this is any measures measures for population, right? And we learned that mu, so mean and sample mean, true mean and sample mean, they measure the center, right? But we also have, when we're talking about statistics, we have three things. We have center, we have spread, and we have shape of a distribution. So when we're doing sample mean, we're obviously talking about the center, and mu as well, we're talking about the center of the distribution. Alright, so we call this parameter anything dealing with the population, the true mean. We call that parameter. But here, when we're taking a sample and we're trying to estimate the population, we call this statistics. And that's where the word statistics comes into play. Statistics is referring to the sample, and parameter is referring back to the population, right? And also, I remember Muema asked a really good question, because in Excel, for sample mean, we use what? We just use mean. Sample mean, and for population mean, we just use the mean. And in Excel, that translates to average, and then you parentheses range. But population is a little tricky. I'm sorry, variation is a little tricky, right? For variance, we have variance.p and variance.sample, right? And these two measures are different. Unfortunately, the formulas are different. Why? And I thought about explaining this theoretically, but I don't think it's a good idea. So I'm going to show you a computer program that kind of explains how they're different, right? So for variance, let me just tell you a little bit about variance. Variance, we take the observation, right? And we subtract the average or the mean, say for variance, so x bar, or it could be mu for population, right? We square it. We take the sum for every single observation, and then we divide it by. Theoretically, if you think about it, if you're averaging the distances, right, where these are the distances between the mean and the observation, theoretically you would square it, because we don't want any negative signs. We square it, and you would think that you would divide it by n, right? Because that makes sense. If you're averaging it out, and if you're looking for a measure, doesn't it make sense to divide it by n, because we have n observations? But that's not true for sample. We always subtract 1 from it. So this is a sample. This is a sample variance. And we note it by s squared, right? Whereas the true population, right, variance of population is a little different in that it's just, oops. Okay, so it's let me just select this again. So it's just sigma of observation minus, instead of sample mean, once we have the population mean, we're going to use that, right? So we're going to have population mean, mu, squared. Here it's going to be n, if this is population. And I'm gonna tell you why. And we call this, okay, we call this sigma squared. right? So before I use the computer program to show you why that is the case, let's just intuitively think. All right, so we subtract 1 from n, right? Then it's going to make this number smaller, right? Smaller. And once we have a smaller number on the bottom, the whole fraction, whole number will be what? Bigger. Bigger than this. And I briefly told you why that is the case. That's because to penalize for small samples, right? So say we have an observations of 10, then that's gonna make a huge difference, being from 10 to 9. But say we have a million, right? Million minus 1, that's not going to make that much of a difference. So that's why we make it -1, and I'll show you using the program why that is the case. And it's really interesting because it shows the pattern, right? So let's move on to the program. Okay, so I'm sorry about that. The program, I'm running a recording program right now, so it's giving me some errors. I just screenshot it here, and let's discuss what this entails. Alright, so what it's doing is it's basically a computer program that runs a model simulation, and here it says the population distribution with n equals 415. Mean is about 10.1 and variance is 30.6, and these are all true statistics, which means that these are parameters. Okay, and since the n was pretty small, we can actually find the mean, right? This is a simulation. They change it every single time you go on it. And if you look at sample statistics here, right? I can't find my pen. Ooh, where is it? Okay, it's right here. So if you look at sample statistics, it says sample variance here. So this is what? This is the S squared, and sample mean right here, this is X bar. Okay? So if you look at these dots, this is the distribution. I would say this is a scatter plot because you see the dot and we have two variables here. So and here is the true mean here. Sorry. So here is it's about 10.1, and here across 32.6. So this is a true mean and true variance, and these are the samples, right? Samples that the computer program used to describe. So sample size versus variance. So when the sample size is 2, so it took all the possibilities of sample size of 2, so which means that sample size equals n, right? So when n equals 2, you take all the averages and all the variances together. So if you look at the sample variance over population variance, so they're comparing the two, the sigma squared and S squared, right? This is what? It's only half the real value, meaning S squared only reaches half of the real variance, and that's not good. We want to be as close as to the real value, which is 100%. And as you increase the sample size, we see that this is going to 100. And here sample variance, this is sample variance using this formula. I'm sorry, I didn't write that down here. Over n instead of n minus 1. And we call this biased variance. So that's why we don't really use it. As you can see here, we don't use it because it's not accurate, right? this is like not even half of the real value. That's why we use n minus 1 instead of n. But if you see the pattern here, right, this is what? N minus 1 over n. Okay, what I mean by that is we see the pattern here. So if the population variance is 100, the sample variance here is about 50. Correct? So that's like half of the real value, and which is 1/2. So that's when n equals 2. So n equals 2, it's half because n minus 1 is 2 minus 1, 1, and n is 2. So this is half of the real mu. Alright, and then the pattern continues as we move forward. So for sample size of 3, this is like 2/3. 2/3 of the real oh, I'm sorry. It's not mu, it should be sigma squared, right? So this is nearly 2/3 of the sigma squared, the real variance. So 2/3 of sigma squared, and that's why we get 2/3, because when n equals 3, this is n minus 1 over n, so 2/3, right? If you continue this pattern, this is so this is a few example using n equals 2 and 3, but it continues until, you know, when theoretically when the sample size reaches infinity. So the statisticians and mathematicians, they came up with the simulation, and they found this this pattern. So you would have to divide by this pattern in order to get the true variance, right? So meaning, if you for sample size of 2, you would have to divide by 1/2. In other words, you're multiplying by 2 to get closer to the true variance, right? So you're dividing by n minus 1 over n, which is essentially multiplying n over n minus 1, and these two cancel out, and that's how we get to this formula that we're using, over n minus 1, and we call this unbiased variance. And when we're talking about sample variance, this is the variance that we're using. This is a formula that we're using, and here we just use this to see why we're not using n, because it's kind of weird that we're using n minus 1, because we're trying to find the really like the average kind of concept, but we're using n minus 1 for that reason. Alright, so that's hopefully that clears up why we're using n minus 1, and just remember that population and sample variance, those are two different things. So to sum that up again, okay, so we call that parameter. This is referring to the true population, right? And the parameters are mu and sigma squared. This is center, right? This is the mean, and this is referring to the spread or the variance. Versus when we're using sample, right, we call this statistics, and we use this to measure the sample, right, and we call this x bar comma s squared, right? So this again, this is the center, and this is a spread. It's measuring the variance and the mean. Alright, so that's the difference between sample and population. Alright, so actually, I finished recording everything, but the file was gone, so I'm re-recording it. So I already have the notes here. So let's just uh, talk about this. So now we're going to talk about correlation and causation, right? So the difference between correlation and causation is that correlation just describes the relationship between two variables, right? So it doesn't necessarily mean that one causes another. It's just stating that there is a relationship. So um, if there is a correlation between the two variables, that means that there is a linear relationship, either positive or negative. There is a relationship going on. But on the other hand, causation is talking about something different, right? So causation is talking about cause and effect. What it means is that one variable causes another, right? So let's just take a look at an example, right? So this is a really simple example. This was actually a study uh, done, and this was the report or the article that was published. And whenever we're looking at these kind of articles, we have to be careful because sometimes they try to use statistics in their favor to I guess get across their point, but knowing statistics, you have to be very careful because they can manipulate not the data but results in a way that is in favor of their opinion, right? So here it talks about how eating breakfast prevents obesity, right? So eating breakfast prevents obesity, but we have to really think about it. So does really does it really prevent obesity? It's not really it's not really a positive like causation. So it doesn't really necessarily cause one or the other. I mean, there is a correlation between the two, meaning that if you eat breakfast, um, you might be less likely to be obese. But you have to look into other factors. For example, so if you're eating breakfast, right, it might be that you are more physically active, right? Sometimes athletes, people who are playing sports, they they are more physically active and thus they are more hungry, so they eat breakfast. And um, being physically active, they it helps them to be more fit and to be lighter and not obese. So that might be another underlying issue that's affecting the breakfast and obesity, and we call that lurking variable, right? So this is kind of it's not the greatest example, but I just wanted to point out that articles do sometimes manipulate the findings. So let's just talk about an easier example. Here we're talking about number of firefighters and amount of damage that is done to the house or building, whatever it is on fire, right? So here there is definitely a positive correlation, right? And I graphed the scatter plot. So on the x-axis we have number of firefighters, and on the y-axis we have amount of damage, right? And I just plotted it in a random way, but there is definitely a a positive relationship going on, correlation going on. But that doesn't necessarily mean that one causes another. For example, um, does does having a lot of firefighters cause more damage? If you think about it, there is a fire, and if you bring in more firefighters, does the house get more damaged? I don't think so, because if that was the case, you would bring in fewer firefighters to lower the damage, right? So it doesn't necessarily cause I'm sorry, the number of firefighters does not necessarily cause the amount of damage that's being done, right? So if you're looking at this, we have to look at the underlying problem, and the underlying problem here is a seriousness of fire, right? So if the fire is serious, you're going to have more firefighters come in, and if it's serious, the amount of damage done will be more, right? So this is the variable that is affecting both of them. And we call this lurking variable because when we're not looking at this part, we're just looking at number of firefighters and amount of damage, then you might think, I mean, there is a correlation, but you might think it doesn't really cause so does the number of firefighters cause amount of damage? No, it's always a seriousness of fire that is affecting both of them, and we call that the lurking variable because it's hidden, it's not shown, but this is the one that's driving both of them, right? So that was um, the discussion of correlation and causation, and also the lurking variable. And now we're going to talk about percentile. All right, percentile. We briefly talked about it when we were talking about quartiles. So the definition is when observations are put in an increasing order, right? Nth percent. Okay, let me just make it a different variable because it might be confusing because we're using n for something else. Let's make it p. Pth percentile means that there are, okay, let me sorry, this has to be p as well. Where is my mouse? Okay, there are p% below or equal to that observation. So it's kind of confusing, the wording, but let's just look at an example. So for example, these are the data sets we have: 2, 2, 3, 4, 5, 5, 5, 6, 6, 7. Alright, these are the data sets. And what we're looking for is the 25th percentile, which is the first quartile. Right? So what that means is that Q1, it just means a number. It's a number, right? So that number equal to that number or below, we have 25% of the data. Okay? So, if you are, so here, at least 25% of the data or 20% of the data lie, okay, let me fix this, lies less than or equal to the observation. Okay, so um uh mm, yes, what, yeah, just let's just continue. So that means that um 20 any so if we come up with the 25th percentile, it's going to be a number along this number line, um equal, the number of observations equal to or less than that number is always greater than 25%. Okay, so it might be a little confusing, but let's just go on with it and give a look at an example. So for example, let's say we're looking at the number 3 here. Okay, and we're wondering what percentile is 3. Okay, so the definition is of percentile is how many observations, okay, how much percent of this whole data set lies below or equal to that number, right? In this case, that's 3. Okay, I'm right here. That's 3. So how many observations are below or equal to 3? That's 1, 2, 3, right? We have 3 observations. So that's 3 out of how many observations we have? N equals 10. So 10. That means that this is 0.3 or 30th percentile. Okay, why? Because we have 3 observations equal to or below the number 3. So that is why the percentile is 30th percentile for this observation 3. And there is a formula for it. So let's say we're looking for the pth percentile. Then that means that we're going to divide p by 100 because this is out of 100%, and multiply that by number of observations, right? N. Oh, sorry, I was there. N plus 1. And this gives you the rank. Okay, what I mean by that is, if we're looking for 25th percentile, it's going to be 25 over 100, right? That's 0.25. And you multiply that by n plus 1, and n in this case is 10, so 10 plus 1 is 11. So we're going to do 0.25 times 11, which is which comes out to be this number, 2.75. I mean, this is not the greatest example, to be honest, because the numbers they overlap, but we're not talking about the real number here. We're not talking about 2.75 as a number, but we're looking at the 2.75th rank. Okay, so we count from the lowest number. So this is 1 and this is 2, and we want 0.75 in between, right? And that would be what? 2.75. That's why the 25th percentile is 2.75, right? Similarly, if we're looking at, alright, so if we're looking at 60th percentile, that's going to be 60 over 100 multiplied by 11, and that comes out to be 6.6. And this is 6.6th rank. So we count off from the lowest number. So 1, 2, 3, 4, 5, 6. And we want 6.6. So we want 0.6 towards the next number, but which is 5. So it's always from here to here, it's always 5 all throughout. That's why the 60th percentile is 5. Right? So hopefully that was clear enough. If you have any questions, we can always go over it during Q&A session. But now I'm going to, you know what? Yeah, why don't we just work another example, because for this problem it was kind of confusing because of the numbers. Let me just come up with another one. So for example, say we had numbers 10, 15, 17, I don't know, I'm just making these up, 20, 20, 21, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know what, let's make it 11. Alright, so these are the data set we have, and we have n equals 11. Right? So let's look at an example. Say we're wondering what percentile this is. 18 is. So what percentile? We're wondering, right? Percentile, then we have to count the number of observations below or equal to that number, right? So this is 1, 1, 2, 3, 4, 5. So that's 5 out of 11, which is about 4, 5, 5. Oops, 5. Okay, so that's about rounded up, you can say 46th percentile, right? And we don't have to worry about the order because this is already in increasing order. Let's flip it and let's say how we're looking for, I don't know, 70th percentile, right? Now we're looking for the observation number, not the percentile. We were given percentile, we're looking for the number, right? So, well, if you use the formula above, that's 70 over 100, and n, which is 11 plus 1, 12, right? If you do this, you get 0.8. Oh, sorry, it's not 0.84. You get 8.4. This is rank. Okay, so let's count up 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is 8. So we're looking at these two numbers. This is 8 and this is 9. And we want 0.4 way towards 30. Okay, so what we're going to do is something called interpolation. So basically what we're doing is we're trying to find the number between 21 and 30 that's of 0.4 away from 21. And how would you do that? Okay, so first off, let me just draw this 21 to 30, but we want not halfway but 0.4. So it'll be 40% of way, and we're looking for this number, right? And this would be 60%. So what do? You just subtract 21 from 30, that's 9. And we just want to divide this number by what? Just divide it by 10. And then multiply by 4. So what we're doing is we're dividing by 10, so that's 0.9, and then we're multiplying this by not 0.4, just 4. So that's 3.6. So 3.6 is this distance, so you would have to add this number to 21. So that's going to be 21 plus 3.6. Okay, so the answer is 24.6 is the answer. Right? So that's pretty much how you calculate percentile. I'm not going to ask you to manually calculate the percentile because Excel already has it, and I don't think there is any need to do that by hand as long as you understand the concept. So going back to the concept again, percentile means something percentile is that there is P% below or equal to that number, the observation. Right? If you have any questions, we can go over in depth and during Q&A session. So I'm gonna show you how to do this on Excel. So this is the data that we worked on for percentile, and let's just do it. It's pretty easy. Let me just delete this first. And I believe Moema asked me before about percentile function, and I told them that you have to use percentile without exe, but that is not true. It turns out that that without exe, that's for Excel 1997 or earlier, and I believe everyone here has a more advanced version than that. So we're just going to use percentile.exe, and then you give it a range, comma. Now it's saying you have to enter k. K value is from 0 to 1. So pretty much it's percentile out of 1. Percentile is always out of 100, but in this case it's out of 1. So if we're looking for, I don't know, 25th percentile, you would put 0.25. Close the parentheses, and here we have the number, same as what we had before, right? If you're looking for median, instead of using quartile or the median function, we can use percentile. And then we have range, comma, it'll be 0.5 because it's right in the middle. Now we have 5. That's what we got before too. Why don't we just do 60th percentile? Give it a range, comma, 60th, so it's going to be 0.6. And we also have 5. That's what we got before. Right? So, I think that's about everything that I wanted to cover or review. Now we're going to move on to the class activity, which is labeled as franchise, right? So if you go to this tab, you are given a data set, as always, and I'm going to explain what this really entails. But before we do that, I want you to take as much time as you can possibly take. Okay? So just take your time doing this. We have a lot of time. All the left over hours are for class activity. So please just work on this. Pause the video and work on it. And once everyone's done with it, or if after you guys are done discussing this problem, then come back to it. Alright, so there is no rush. Just take your time. But just to explain what's going on, here we have X and Y. X equals annual franchise fee in $1,000, and Y equals startup cost in $1,000. Right? So X, for example, if you're opening a McDonald's and you have to pay for the franchise fee, so you have to pay certain amount of money to McDonald's, and also you need startup costs when you're opening the business. You need other stuff like renting or buying a broker or dealing with legal documents, buying a lawyer. All these things, they sum up to the startup costs. So pretty much in this data set, we're looking at the relationship between X and Y, the franchise fee and the startup cost. Alright, so please work on the questions here and come back to it when you're done with it, whenever you're done with it. Okay? So please do that.